A large asteroid will safely zoom between Earth and the Moon on Saturday, a once-in-a-decade event that will be used as a training exercise for planetary defense efforts, according to the European Space Agency. The asteroid, named 2023 DZ2, is estimated to be 40 to 70 meters, 130 to 230 feet, wide, roughly the size of the Parthenon, and big enough to wipe out a large city if it hit our planet. It will come within a third of the distance from the Earth to the Moon, said Richard Moisel, the head of the ESA's Planetary Defense Office. Though that is very close, there is nothing to worry about, he told AFP. Small asteroids fly past every day, but one of this size coming so close to Earth only happens around once every 10 years, he added. The asteroid will pass 175,000 kilometers, 109,000 miles, from Earth at a speed of 28,000 kilometers per hour, 17,400 miles per hour. The Moon is roughly 385,000 kilometers away. An observatory in La Palma, one of Spain's Canary Islands, first spotted the asteroid on February 27. Last week, the UN-endorsed International Asteroid Warning Network decided it would take advantage of the close look, carrying out a rapid characterization of 2023 DZ2, Moisel said. That means astronomers around the world will analyze the asteroid with a range of instruments such as spectrometers and radars. The goal is to find out just how much we can learn about such an asteroid in only a week, Moisel said. It will also serve as training for how the network would react to a threat, possibly heading our way in the future, he added. Moisel said preliminary data suggests 2023 DZ2 is a scientifically interesting object, indicating it could be a somewhat unusual type of asteroid. But he added that more data was needed to determine the asteroid's composition. The asteroid will again swing past Earth in 2026, but poses no threat of impact for at least the next 100 years, which is how far out its trajectory has been calculated. Earlier this month, a similarly sized asteroid, 2023 DW, was briefly given a 1 in 432 chance of hitting Earth on Valentine's Day 2046. But further calculations ruled out any chance of an impact, which is what normally happens with newly discovered asteroids. Moisel said 2023 DW was now expected to miss Earth by some 4.3 million kilometers. Even if such an asteroid was determined to be heading our way, Earth is no longer defenseless. Last year, NASA's DART spacecraft deliberately slammed into the pyramid-sized asteroid Dimorphos, significantly knocking it off course in the first such test of our planetary defenses. How did life come about? The answer to this question goes to the very heart of our existence on planet Earth. Did life simply arise from chemical reactions among organic compounds in a primordial soup left after Earth clumped together from space rubble? If so, where did the organic compounds come from? Some of the so-called building blocks of life may have been surprisingly common in the early solar system. A team of Japanese and American scientists led by Yasuhiro Oba has analyzed samples taken from the asteroid Ryugu in 2018 by the Hayabusa 2 mission and found uracil, one of the 5 key bases of the RNA and DNA molecules that are crucial to life as we know it. Their study was published March 21 in Nature Communications. At the most basic level, the development of life is a matter of combining simple organic molecules into increasingly complex compounds that can participate in the myriad reactions associated with a living organism. Simple amino acids are believed to act as building blocks in the construction of these more complex molecules. But this isn't just a simple random combination exercise. The largest chunk of the human genome, chromosome 1, is made up of 249 million base pairs, the rungs on the twisted ladder of the DNA molecule. Each base pair is made of 2 bases, either guanine and cytosine, or adenine and thymine. Building from the simple base pair chemicals to a full strand of DNA is a massive undertaking. A strand of DNA also has a complex structure, which varies from one individual to another. Life on Earth uses the structure of DNA to memorize the construction of the life form involved. Alongside DNA, life uses a molecule called RNA for making proteins and doing other odds jobs inside cells. RNA is also made of a long string of bases, guanine, cytosine and adenine, like DNA. But instead of thymine it has uracil, which is what turned up in the sample from Ryugu. Ryugu is what's called a C-type or carbonaceous asteroid. These are the most common type in the asteroid belt, making up about 75% of the asteroids we can see. The Hayabusa 2 mission established that C-type asteroids like Ryugu are the source of a kind of rare meteorite sometimes found on Earth, called a carbonaceous chondrite. Uracil and other organic molecules have previously been found in these meteorites, but there has been no way to rule out the possibility that some of the molecules had a terrestrial origin. The meteorite samples could have been contaminated here on Earth, or their chemistry might have been changed by heating as they fell through the atmosphere. However, since the Ryugu sample was taken from the surface of an asteroid and brought back in a tightly sealed container, scientists are confident it is free of contamination or any effects of coming to Earth. Furthermore, the presence of these amino acids on Ryugu shows that even on asteroid surfaces, exposed to solar wind, micrometeorites and cosmic rays, organic molecules can survive transportation through the solar system. A huge variety of different organic compounds have already been found in Ryugu samples. Many organic molecules, such as amino acids, come in two forms: left-handed and right-handed. Life on Earth relies on left-handed amino acids, but both forms are equally common in Ryugu samples, which indicates the molecules found on Ryugu are not signs of life. The solar system formed around 4.57 billion years ago from a molecular dust cloud that was exposed to UV radiation and particle bombardment from protons. The molecular cloud contained simple molecules such as methane, carbon tetrahydride, water, hydrogen oxide, and ammonia, nitrogen trihydride. These would have been fragmented by the radiation, and the fragments would have reassembled into more complex molecules such as amino acids. C-type asteroids like Ryugu are believed to have formed so far from the Sun that the water and carbon dioxide they contain would have remained frozen. However, as the asteroids warmed up and the ice melted, liquid water would have been able to react with the rocks and minerals. Whether these conditions led to the creation of more complex organic molecules is an open question, but certainly these conditions would be conducive to further reactions. In addition, these conditions could affect the survival of different compounds. The Hayabusa 2 samples from Ryugu provide a new context for understanding the origin of organic compounds that may have been the start of life on Earth. It is still a big step from having these organic compounds available to early Earth.